In our time, man's technology has thrust him farther and farther away from Earth. First, our age witnessed the development of the airplane, from propeller-driven to jet experimental craft, streaking at supersonic speeds at the very top of the atmosphere. And finally, we have witnessed manned spacecraft hurtling through the void beyond the atmosphere. Indeed, the spectacular advance in man's knowledge of near and outer space has been quickly accomplished. Yet, oddly enough, man knows relatively little of the very atmosphere he lives in. By this is meant the first 3,000 feet above the Earth's surface, be it over oceans or mountain peaks, a chaotic and complex region. In this layer, tremendous energy transfers occur between the sun's rays and the atmosphere, between the atmosphere and the Earth, and between the sun's rays and the soil and bodies of water. It is in the lowest part of the atmosphere, called the boundary layer, that we spend most of our lives. Here, at the bottom of our ocean of air, we experience the more pronounced expressions of nature. Tranquil summer days, peaceful moonlit nights, gentle breezes, howling high winds, stifling dust storms, spring showers, threatening thunderstorms, raging floods, and, sad to say, one of man's modifications of nature, the smog of our cities. In arid sections of the country, the air pollution in the cities is primarily smoke, most pronounced during nighttime. Whereas in more humid areas, air pollution is frequently a combination of smoke and fog, commonly called smog. Yes, all of us, layman and scientist alike, are familiar with the everyday faces of nature here in our life-giving boundary layer. Yet not even the scientists fully understand the physical processes at work, the meteorology, that is, of the air around us. As we learn more of these processes, aside from satisfying scientific curiosity, we should be able to solve a number of practical problems. For instance, meteorologists predict large-scale weather changes by solving complex equations. Such equations explain the general motion and condition of the atmosphere, but they do not sufficiently take into account all the physical effects of the boundary layer. So to understand fully the whys and hows of air pollution, we must learn more about this lowest of layers. This is also true if we are to master techniques for control of the distribution of rainfall. If we are to understand the effects of the interaction of atmosphere and soil and plant life. And if we are to learn more about atmospheric effects on the propagation of light, sound, and radio waves near ground level. There are also numerous military needs for increased knowledge of the boundary layer. For instance, the accuracy of artillery depends upon accurate prediction of low-level atmospheric conditions. The development of sound ranging systems to locate the origin of enemy artillery fire depends upon accurate determination of temperature and wind data over the sound wave path. The causes and dynamics of air turbulence, an important factor in military aircraft operations, are only partly understood. The diffusion pattern of toxic gases from exotic missile fuels is of interest in order to protect personnel. And finally, the effects of the lower atmosphere upon the trajectory of guided missiles and free-flight rockets are of paramount military importance. At White Sands Missile Range, the U.S. Army Electronics Command, responsible for meteorological R&D, has conducted intensive studies on the effects of the boundary layer upon military operations. These studies are conducted by the Atmospheric Sciences Laboratory, an element of the Electronics Command, Army Materiel Command. The complex nature of the boundary layer makes the job difficult. For example, let's take a broad look at some major phenomena at work in the lower atmosphere. The atmosphere receives water vapor from vegetation, from lakes and ponds, and from the sea. Heat from the sun warms the earth and is in turn released into the atmosphere. And mechanical friction between air and ground constantly applies a brake to atmospheric motion. The interactions of these and other phenomena, covering an area as big as all outdoors, are of an extremely complex nature. For convenience, the boundary layer is divided into the surface boundary layer, approximately 100 feet thick, and the planetary boundary layer, about 3,000 feet thick. To take meteorological measurements of the surface boundary layer, the Atmospheric Sciences Laboratory maintains several instrumented 500-foot towers. Note that at the moment, all vanes indicate the same wind direction. In fact, tower data indicate that over flat terrain, generally the average wind direction does not change significantly with height in the first 100 feet, except in stable air. Now the wind vanes react to turbulence, a term meaning that fluctuations in both wind speed and direction are taking place, both vertically and horizontally. This graph, recorded from the tower-mounted instruments, shows a relatively constant, strictly horizontal wind direction. As an illustration of this condition, smoke from a chimney travels in predominantly one direction and tends to form a heavy concentration. Here, the graph shows continuous changes in wind direction. Such changes cause the smoke to move both horizontally and vertically and to spread over a large area. All studies have indicated that variations in wind direction, horizontal and vertical, are the primary factor influencing the diffusion of fuel-produced gases and other pollutants into the air. as well as toxic rocket fuel residues released during missile firings. Fluctuations about the average wind speed and direction traces define the degree of turbulence or wind variability. If direction fluctuations amount to only a few degrees, as shown here, the intensity of turbulence is said to be low. If the variability is high, say 30 or even 80 degrees, then the turbulence intensity is high. Now to consider fluctuations in wind speed. Note that the speed changes with time. The peaks are referred to as gusts and the troughs as lulls. Note that if turbulence intensity is high, the wind changes are large. Wind tunnels offer another demonstration of turbulence. When laminar flow is smooth, as shown here, turbulence is said to be absent. But when the degree of variability is large, the intensity of turbulence is high. Here, the smoke movement is slowed by the camera. It should be remembered that atmospheric turbulence is not always gentle. For example, this B-52 bomber's stabilizer was torn away by clear air turbulence in the lee of a mountain range. Usually, we think of the wind as blowing horizontally at a given speed. In fact, the air moves vertically as well as horizontally. A point of interest is that the vertical motions average out to near zero over a large geographical area or over a long time interval. That is, the mass of air that goes up equals that which comes down, except over sloping terrain. Hence, individual vertical fluctuations are of greater significance than the average of all fluctuations for most practical applications. One example, vertical motions play a key role in carrying water vapor and heat into the atmosphere, and also transporting wind energy from the atmosphere to the ground, a process called friction. On a clear day, the vertical motions are relatively large. The visible extreme is the dust devil. At night, these motions are very small. These irregular vertical fluctuations of the wind, along with the horizontal ones, are called turbulence. There are two major kinds of turbulence, mechanical and convective. Convective turbulence occurs when heat is convected from the ground to the atmosphere. The ground receives its heat from the sun, the atmospheric temperature being little affected by direct solar radiation. Some parts of the ground absorb more heat than others. Over the warmer areas, the air ascends in eddies on buoyant plumes called thermals. When dust is carried upward, as here, they are known as dust devils. And here is the most extreme form of thermal, the dreaded tornado. Thermals are sought by sailplane pilots in order to reach great altitudes. Birds have learned the technique. As have skydivers. Thermals may consist of large upward motions. For instance, the tops of fair weather cumulus clouds are often formed by thermals when enough moisture is present. By way of simplification, the air rises in the center of a typical thermal and falls around its perimeter, forming in effect a closed vertical circulation system. If the air is also in horizontal motion, the thermal may be carried along with it. As illustrated in the wind tunnel, convective turbulence is not well organized in reality, but occurs in many sizes and shapes. Therefore, as the Army studies at White Sands have borne out, wind changes observed at a single point in the thermal are not regular, but chaotic, that is, turbulent. Mechanical turbulence, the second major kind, amounts to a physical stirring of the atmosphere. In the boundary layer, mechanical turbulence may be produced by wind blowing over rough terrain. The rougher the ground, the stronger the turbulence. Turbulence is particularly noticeable in an airplane alternately passing over rough and smooth terrain at a fairly low altitude. Also on a large scale, wind flow over large obstacles such as a mountain range produces lee waves, here greatly accelerated by the camera. Sometimes a large-scale circular motion develops, a form of turbulence called a rotor. Purely mechanical turbulence is most common on windy days with thick overcasts. Clear skies with some wind produce a combination of convective and mechanical turbulence. On clear nights, the ground grows colder than the air above it, and thermals are not generated. However, mechanical turbulence may be present, provided a fairly strong wind is blowing. The major role of turbulence in influencing the behavior of the boundary layer is the mixing of fluids with different characteristics. For example, note that at first the cream and coffee mix only slightly, but stirring creates mechanical turbulence, which produces a uniform mixture. Now to consider how this mixing example applies to the atmosphere. When cold air moves over warm ground, the air in contact with the ground quickly tends to take on the ground temperature. Mixing produces a sudden rise in air temperature nearest the ground. However, the mixing is performed by eddies of so small a scale that quite large temperature differences may exist in the first few feet. At higher levels, the temperature decreases more gradually and may become fairly uniform as a result of greater mixing efficiency. In general, rapid changes with height of meteorological variables can occur only near the surface. Now consider again the case of cold air over warm ground. Here, vertical motion carries cold air downward and hot air upward. When dry air is located over a body of water, a thin layer of saturated air is found immediately above the surface. Drier air, brought down by vertical mixing, reduces the vapor in the surface layer and speeds up evaporation. The greater the turbulence, the greater the evaporation. Studies of wind speed in relation to turbulence have shown that typically winds of high speed come down to the surface, while winds of low speed rise from the surface. Vertical winds going upward because of mechanical turbulence induced by surface friction are strongest near ground level, but steadily decrease in strength with height as the effects of ground friction decrease. Conversely, it has been found that the speed of horizontal winds at 2 feet is substantially slower than it is at 12 feet. However, because of the small size of mechanical eddies near the surface, much less difference in speed is found between 12 and 22 feet. With increase in height, the eddies become convective, larger, and more efficient mixing agents. Now for some practical applications based on an understanding of turbulence in the boundary layer. Let's begin with atmospheric pollution. Commonly, smoke expelled at night moves very little vertically, but tends to spread in a horizontal layer. When the sun rises, it heats the ground, producing convection, which causes vertical motion. Smoke or harmful gases may be either brought down or carried upward. The downward phase of this process is called fumigation. Under such conditions, a single source can spread pollutants over many square miles. A more favorable condition results when, particularly during the day, the vertical motion carries the pollutants upward and disperses them at higher altitudes. So much for the surface boundary layer. Now let's turn to the 3,000-foot-high planetary boundary layer. Unfortunately, relatively few scientific observations have been made of this region. One reason is that few meteorological towers extend over 1,000 feet, and fewer still are sufficiently instrumented. Most weather balloons travel too fast through the planetary layer to give readings on wind, pressure, humidity, and temperature in enough detail. While some information has been gathered using helicopters, various types of special balloons, and smoke trails, a great deal remains to be learned about the distribution of wind, heat, and moisture, and the exchange processes controlling their distribution in this region. However, limited knowledge of the planetary boundary layer has been gained. For instance, above 100 feet, the deflecting force due to the Earth's rotation is more pronounced. This Coriolis effect turns the wind clockwise in the northern hemisphere. Typically, instead of the stable wind direction found in the surface layer, we find that with increasing height, the wind speed normally accelerates and changes direction. The angle between surface winds and those at about 3,000 feet is typically 30 degrees. Over water, normally a smooth surface, the angle is typically 15 degrees, turbulence not being as strong. However, there are many variations from these conditions. One significant variation usually occurring at night is the low-level jet, a high-velocity ribbon-like wind at about 2,000 feet. This wind results from an effect of the daily cycle of solar heating and the resulting daytime variation in vertical mixing and internal friction. On clear nights, when there is very little vertical exchange of air, the air near the ground becomes colder than the air above it, a condition known as an inversion. The absence of vertical mixing results in a condition of near calm close to the ground, while at about 2,000 feet, the wind is much faster than normal, sometimes faster than the wind above that level. Normally, winds near the ground are fastest in the middle of the day and slowest at night. But at 2,000 feet, opposite conditions frequently prevail. For here, winds are fastest at night and slowest in the day. At a given time, the wind at 2,000 feet may be blowing at 50 miles per hour, while on the ground, the wind is light. Lack of knowledge of this condition has resulted in the loss of many balloons involved in studies of the upper air. Another practical problem requiring knowledge of the planetary layer is faced by aviators engaged in landing when high winds are blowing at 2,000 feet while ground wind is light. A rapid loss of airspeed results in the last few hundred feet, a condition requiring a special alertness on the part of the pilot. Incidentally, here we see another phenomenon of the surface boundary layer, scintillation or abnormal light refraction, resulting from abnormal temperature distribution. To summarize present knowledge of the physical processes of the entire boundary layer, though limited, is of practical value in solving problems in such areas as prediction of weather on a global scale. Reduction of air pollution in our cities. Improvement of plants to increase the world's food supply. Navigation of aircraft to avoid excessively turbulent air. Improved transmission of electronic signals through the atmosphere. Greater accuracy of artillery. Determination of diffusion patterns of toxic gases. And the influence of low-level wind upon the trajectory of missiles. In closing, these have been highlights of our present knowledge of the meteorology of the first 3,000 feet of the atmosphere. Also presented have been some of the practical problems depending for solution upon expansion of our present body of knowledge. To assure that such an expansion is realized is the goal of meteorologists in many fields of application, including scientists of the Army Electronics Command Atmospheric Sciences Laboratory at White Sands Missile Range, whose past contributions to the meteorology of the lower atmosphere have been substantial.